Welcome to this video. Today, we'll be solving a fascinating problem titled The Maze, problem number 490. We'll explore the challenge, break it down step by step, and discuss different approaches to solve it. Let's dive in and sharpen those problem-solving skills. In this problem, we are working with a maze represented by a two-dimensional binary grid. The cells in the grid can either be open spaces, denoted as 0, or walls, denoted as 1. You are given the starting position of a ball, represented by the coordinates start_x, start_y, and a destination position, destination_x, destination_y. Both the starting point and the destination point are guaranteed to be open spaces within the maze. The ball can move in any of the four cardinal directions up, down, left, or right, but it doesn't stop at each step. Instead, the ball rolls in the chosen direction continuously until it hits a wall or goes out of bounds. Once it stops, it can choose the next direction to roll in. The task is to determine whether the ball can ultimately stop at the destination position. If it can, we return true, otherwise, we return false. To better understand the problem, let's look at an example. Here, we have a 5x5 maze grid where cells marked as 0 are open spaces and cells marked as 1 are walls. The ball starts at position 0, 4, which is the top right corner of the grid, and the destination is 4, 4, which is the bottom right corner. The output for this input is true, indicating that the ball can successfully reach the destination. In this example, the ball begins at 0, 4, and rolls as follows. First, it moves left until it reaches 0, 0, the far left edge of the maze. Then, it rolls downward, stopping at 4, 0, the bottom left corner. Finally, the ball moves right and reaches 4, 4, which is the destination. Since the ball successfully reaches the destination, the output is true. Now consider a second example where the ball starts at the same position, 0, 4, but the destination is 3, 2. In this case, the output is false because there is no valid path that allows the ball to stop exactly at the destination coordinates. For the second example, the ball starts at 0, 4, but cannot reach the destination, 3, 2. The layout of the maze prevents the ball from stopping at 3, 2, as all possible paths either hit walls or bypass the destination entirely. Now, let's consider a third example. Here, the maze layout is different, and the ball starts at 0, 0, the top left corner of the grid. The destination is 4, 4, the bottom right corner. The output for this example is true, meaning the ball can successfully reach the destination. In the third example, the ball starts at 0, 0, and rolls as follows. First, it moves right until it reaches 0, 4, the top right corner. Then, it rolls downward to 2, 4. From there, it continues rolling down to 4, 4, which is the destination. Since the ball successfully reaches the destination in this case, the output is true. Now let's discuss the constraints of the problem. The dimensions of the maze are defined by m and n, where both values are between 1 and 100. Each cell in the maze is either 0 or 1. The starting and destination coordinates are always valid open spaces, and they fall within the bounds of the maze. Finally, let's consider some edge cases. If the ball starts at the destination, we can immediately return true since it's already where it needs to be. On the other hand, if the maze has walls completely blocking the destination, it's impossible for the ball to reach it, so we return false. In cases where the maze consists of only one open space, if the start and destination are the same, we return true, otherwise, it's false. Lastly, the ball rolling infinitely without hitting a wall is not a concern because the constraints and proper handling of visited positions ensure that such situations are avoided. These edge cases help solidify our understanding of how to handle different scenarios within this problem. To begin, let's consider the brute force approach, which relies on an exhaustive search to navigate the maze. The main idea here is to explore all possible paths from the starting position to the destination by using either a depth-first search or breadth-first search. With DFS, we recursively roll the ball in each of the four directions until it hits a wall, and then backtrack to explore alternate paths. Alternatively, BFS can be employed to explore the maze layer by layer. However, this approach is computationally expensive, as the ball might traverse the entire maze in each direction. This results in a time complexity of approximately m*n*, max, m, n, where m and n are the maze dimensions. The primary drawback of this method is its inefficiency for large mazes, as it redundantly explores previously visited positions, making it impractical for real-world scenarios with complex layouts. To address the inefficiencies of the brute force approach, we can optimize the search by incorporating memorization to avoid redundant exploration. Here, the idea is to track visited positions and directions, ensuring that each position is processed at most once for each direction. This dramatically reduces the amount of repeated work. In practice, we use a visited set to keep track of already processed positions. As the ball rolls in a given direction until it hits a wall, we either recursively explore further in the case of DFS or add the stopping position to a queue in BFS for iterative exploration. This optimization reduces the computational overhead compared to the brute force approach, though the time complexity remains similar. The space complexity is O(m*(n) due to the visited set. A more advanced option is a Dijkstra-like approach, which treats the maze as a weighted graph where rolling distances are the weights. With this method, a priority queue helps ensure that paths with shorter rolling distances are expanded first. However, this technique is more complex to implement, and for unweighted problems like this one, its benefits may not justify the added complexity. Given the nature of the problem, our chosen strategy is to use an optimized BFS approach. BFS is simpler to implement than Dijkstra's algorithm and is particularly suited for this scenario because all rolls are treated equally, making the problem effectively unweighted. The critical realization here is that the ball rolls continuously in a direction until it hits a wall, which allows us to skip over intermediate cells during each roll. This insight significantly reduces the state space we need to explore. BFS's layer-by-layer exploration ensures that we identify the shortest path first, making it more efficient than DFS for this type of problem. Additionally, BFS is easier to debug and maintain compared to Dijkstra's algorithm, which introduces unnecessary complexity in this case. While Dijkstra is ideal for weighted edges, it's overkill here, as all rolls are unweighted. This approach balances efficiency, simplicity, and maintainability, making it the most practical choice for solving this problem. Now, let's outline the algorithm for our optimized BFS approach. We start by initializing a queue with the starting position of the ball. To prevent redundant exploration, we use a visited set to track the cells we've already processed. For each position in the queue, the ball is rolled in all 4 possible directions until it hits a wall. The stopping position is then added to the queue if it hasn't been visited yet. This process continues until the queue is empty or the destination is reached. Comparing BFS to DFS, BFS is preferred here because it explores layer by layer, guaranteeing that the shortest path is found first. While Dijkstra's algorithm also ensures shortest paths, it introduces extra complexity by handling weighted edges, which isn't necessary in this problem. Regarding space complexity, both BFS and DFS require O(m*(n) to store the visited set, making them equally memory efficient. In terms of time complexity, all approaches have similar worst-case scenarios, but BFS with visited tracking minimizes redundant work, making it faster in practical applications. This combination of efficiency and simplicity is why BFS is the ideal choice for solving the maze problem. To solve this problem, we need to navigate a maze represented as a grid, where each cell is either an open path or a wall. The goal is to determine if a ball can roll from a given start position to a destination. The ball rolls in straight lines until it hits a wall, and it cannot change direction mid-roll. This means we need to systematically explore all possible paths to determine if the destination is reachable. One intuitive approach to solve this is using depth-first search, or DFS. This method allows us to recursively explore all potential paths. At each step, we roll the ball in one of the 4 cardinal directions up, down, left, or right until it hits a wall. From there, we backtrack and explore other directions. The process begins by initializing the state. We create a stack or use recursion to simulate DFS, and we maintain a visited set to track cells we've already processed, avoiding infinite loops. The exploration itself starts at the given position, simulating the rolling of the ball in each direction until it either hits a wall or goes out of bounds. If the ball stops at the destination, we return true, indicating the path is valid. If the ball stops at a position that hasn't been visited yet, we mark it as visited and recursively explore further from there. If no valid path is found from the current position, we backtrack to the previous state and continue testing other directions. Once all possible cells have been explored, we return false if the destination remains unreachable. This systematic exploration ensures that all paths are checked. The implementation begins with a helper function to simulate the rolling of the ball. This function moves the ball in the given direction until it either hits a wall or goes out of bounds, returning the stopping position. The main DFS function starts by checking if the current position has already been visited. If it has, we return false to avoid reprocessing. If the current position matches the destination, we return true, as the path is valid. Otherwise, the position is added to the visited set, and exploration continues. In the DFS function, we explore all 4 directions: up, down, left, and right. For each direction, we use the helper function to simulate the ball's movement until it stops. If a recursive call to the DFS function from the new stopping position returns true, we know the destination is reachable, so we can stop further exploration. If none of the directions lead to the destination, the function returns false, signaling that no valid path exists from the current state. This algorithm is built on key insights. First, DFS is well suited for this problem because it allows us to exhaustively explore all potential paths while leveraging recursion for natural backtracking. To handle infinite loops, we use a visited set to ensure that the same position isn't processed multiple times. Additionally, simulating the ball's movement until it hits a wall simplifies the logic, as we only need to focus on stopping positions rather than intermediate steps. The algorithm relies on a few essential data structures. A visited set is used to keep track of processed cells, preventing redundant calculations and infinite loops. The stack, which is implicit in the recursive DFS implementation, helps manage the current state during exploration and facilitates backtracking. To optimize performance, we implement an early exit condition. As soon as the destination is reached, the search stops, saving unnecessary computation. Another optimization is directional rolling, where the ball moves in bulk in one direction until it hits a wall, rather than moving step by step. This reduces computational overhead by eliminating redundant checks. For the time complexity, in the worst-case scenario, every cell in the maze is visited, and for each visited cell, the ball is rolled in all 4 directions. This results in a time complexity of O(m*(n), where m and n represent the maze dimensions. The space complexity is also O(m*(n), as the visited set in the recursion stack can grow proportionally to the number of cells in the maze. To ensure robustness, the algorithm accounts for several edge cases. If the start and destination positions are the same, we can immediately return true without further exploration. If all cells in the maze are walls, there are no valid paths, so we return false. Similarly, if the destination is completely surrounded by walls, it is unreachable, and the result is false. In mazes with multiple paths, the algorithm ensures that all paths are explored, making it comprehensive for finding any valid route to the destination. By systematically handling these scenarios, the algorithm becomes reliable for a wide range of maze configurations, ensuring correctness and efficiency in solving the problem. To solve the maze problem, we start by importing the DEET class from the collections module, which we'll use to implement a breadth-first search, or BFS. Inside the solution class, the hasPath method takes the maze, the start position, and the destination as input. We first determine the number of rows and columns in the maze and define the 4 possible movement directions: right, down, left, and up. These are represented as coordinate changes in a list. Next, we initialize a set called visited to keep track of positions we've already explored, so we don't revisit them unnecessarily. The nested can_roll function is essential. It simulates the ball rolling in a specific direction until it hits a wall. Within this function, we continuously update the position of the ball as long as it stays within the bounds of the maze and doesn't encounter a wall. Once it can no longer move further in the given direction, we return the position where it stopped. We then initialize a queue with the starting position, using the DEET class, and mark the start as visited. The BFS loop begins by dequeuing the current position, and we check if it matches the destination. If it does, we return true, indicating that a path exists. Otherwise, we explore all possible directions using the can_roll function to find the next stopping points. If the stopping position in the current direction hasn't been visited yet, we mark it as visited and enqueue it for further exploration. This ensures that we systematically explore all accessible paths in the maze without revisiting positions unnecessarily. Once all possible moves have been processed, and if the queue becomes empty without reaching the destination, we return false. This means there is no valid path from the start to the destination. By implementing BFS in this way, we ensure that the shortest path, if it exists, will be found. The visited set prevents infinite loops by avoiding revisits, and the can_roll function effectively handles the unique rolling behavior of the ball in the maze. This completes the Python implementation of the solution. Here, we begin with the Java implementation of the maze problem. First, we import the necessary libraries, including java.util*, to use data structures like queues and sets. Next, the hasPath method is defined, which takes the maze grid, the start position, and the destination position as inputs. Inside the method, we determine the number of rows and columns in the maze and define the possible movement directions right, down, left, and up using a 2D array. To track visited positions, we use a hash set, storing coordinates as strings for easy lookup. Then, we initialize a queue to handle the breadth-first search, adding the starting position and marking it as visited. The core of the algorithm involves processing positions from the queue. For each position, we check if it matches the destination. If it does, we return true and stop further exploration. Otherwise, we iterate through each possible direction to explore the maze further. Before moving, we prepare to roll in a direction until we hit a wall or boundary. Now, to simulate rolling in a direction, we use a while loop. The loop continues as long as the next position in the current direction remains within the maze boundaries and does not hit a wall, represented by a 0 in the maze grid. We update the coordinates NX and New York to move step by step in the chosen direction. Once the ball stops rolling, we check if the new position has already been visited. If it hasn't, we mark it as visited by adding its coordinates to the hash set and enqueue this new position for further exploration. This ensures that we don't revisit the same position and get stuck in infinite loops. After exploring all possible directions and processing all reachable positions, if we haven't returned true yet, it means the destination is not reachable from the start, and we return false. This completes the breadth-first search implementation for the maze problem. In this example, we have a simple maze with a straight path to the destination. The maze is represented as a grid where 0 indicates open spaces and 1 indicates walls. The starting point is at the top right corner of the grid, at position 0, 4, and the destination is at the bottom right corner, 4, 4. We begin by initializing some key variables. The number of rows and columns in the maze is determined as 5 each, and we define the 4 possible directions of movement, right, down, left, and up. A queue is set up with the starting point, 0, 4, and a visited set is initialized to keep track of cells we've already processed, starting with the same position. This setup allows us to explore the maze systematically using a breadth-first search approach. The algorithm starts by dequeuing the first position, which is 0, 4. From here, we evaluate all possible directions of movement. Moving to the right hits a wall immediately, so we discard it. Moving down allows the ball to roll straight to the bottom of the column, stopping at 4, 4, which is our destination. Since the destination is reached, we can immediately return true, indicating that there is a valid path. This straightforward example demonstrates how the algorithm effectively handles movement in open spaces and identifies when the destination is reached. Now, in the second example, the maze includes obstacles that block certain paths, making the solution more complex. The starting position remains 0, 4, while the destination is now 3, 2. As before, we initialize the number of rows and columns, the directions of movement, the queue with the starting point, and the visited set. The first position dequeued is 0, 4. Checking all directions, we find that moving right hits a wall. Moving down allows the ball to roll to 4, 4, so we enqueue this position. Moving left lets the ball roll to 0, 0, so we enqueue that as well. Moving up is invalid because it goes out of bounds. The queue now contains 4, 4, and 0, 0, ready for further exploration. Next, we dequeue 4, 4, and evaluate its possible moves. Moving right or down hits walls, while moving left allows the ball to roll to 4, 0, which we enqueue. Moving up brings the ball back to 0, 4, but since it's already visited, we skip it. The queue is then updated to contain 0, 0, and 4, 0. The next position dequeued is 0, 0. From here, moving right returns to 0, 4, which is already visited. Moving down brings the ball to 4, 0, which is also already visited. Moving left hits a wall, and moving up is out of bounds. This leaves the queue with just 4, 0. Finally, we dequeue 4, 0, and evaluate its moves. Rolling right leads to 4, 4, which is visited. Moving down or left hits walls, but moving up rolls the ball to 3, 2, the destination. The destination is reached, so we return true. By reaching the destination at 3, 2, we confirm that a path exists through the maze despite the obstacles. This example highlights how the algorithm systematically explores all possible paths, even when some routes are blocked. It efficiently tracks visited positions to avoid redundant checks and uses the queue to manage the order of exploration. With this structured approach, the solution ensures that the shortest path to the destination is found as soon as possible. Now, let's consider a case where no path exists to the destination. In the third example, the maze remains the same, but the destination is now 3, 0, which is surrounded by walls. The initialization of variables is the same as before. During exploration, the algorithm proceeds to check all reachable cells, just as in the previous example. However, no matter how the ball rolls, it cannot reach 3, 0, because it is entirely enclosed by walls. After exhausting all possible paths, the algorithm concludes that the destination is unreachable and returns false. This demonstrates how the algorithm correctly identifies when a path does not exist, ensuring reliability in all scenarios. Here, we analyze the time complexity of the algorithm. Since we use a breadth-first search, every cell in the maze is visited at most once, which is controlled by the visited set. For each cell, the algorithm explores all 4 possible directions: right, down, left, and up. Now, in any given direction, the can_roll function allows the ball to roll until it hits a wall. This rolling process takes time proportional to the maximum dimension of the maze, which is the larger of the number of rows or columns, denoted as O, max, m, n. In the worst-case scenario, the BFS will visit all accessible cells, which is at most m multiplied by n, the total number of cells in the maze. Additionally, for each of these cells, rolling in all 4 directions adds a factor of 4 times O, max, m, n. Combining these, we obtain a total time complexity of O, m** n, as constant factors are ignored in big O notation. This ensures the algorithm scales efficiently with the size of the maze. Now let's break down the space complexity of the algorithm. First, the visited set is used to keep track of all cells that have been processed. In the worst case, where all m multiplied by n cells are accessible, the visited set will require O, m** n, space. Second, the BFS queue, which holds the cells to be processed, can also grow to hold up to m multiplied by n cells in the worst case, leading to another O, m** n, space requirement. Finally, we have auxiliary storage, such as the list of directions and variables used for rolling, like x, y, dx, and dy. These require a constant amount of space, denoted as O1. When we combine these components, the total space complexity of the algorithm is O, m** n, which remains efficient even for larger mazes. Let's now look at the best, average, and worst-case scenarios for this algorithm. In the best case, the destination is the same as the start position. Here, the algorithm terminates immediately, requiring only O1 time and O1 space since no additional cells are processed. In the average case, the time and space complexity depend on the maze's structure and how walls are distributed. Typically, the algorithm will explore a subset of accessible cells, denoted as K, where K is less than or equal to m multiplied by n. This gives a time complexity of O, K, and a space complexity of O, K, due to the visited set in Q. Finally, in the worst case, where all cells are accessible, the BFS must explore the entire maze. This results in the maximum time complexity of O, m** n, and space complexity of O, m** n. These bounds ensure the algorithm performs consistently across different maze configurations. To better understand the efficiency of the BFS approach, let's compare it to a naive method. A naive approach might explore all paths recursively without marking visited cells, leading to exponential time complexity of O for caret m asterisk n, as the same cells are revisited repeatedly. In contrast, the BFS optimization used here is much more efficient. By using the visited set, we ensure that each cell is processed at most once. Additionally, the algorithm limits exploration to reachable cells only and uses the can_roll function to roll directly to the next stopping point, skipping unnecessary intermediate steps. This drastically reduces redundant computations. The proof of the big O analysis confirms that the visited set contributes O, m asterisk n, and rolling in 4 directions from each cell only adds a constant factor. Together, this keeps both time and space complexity at O, m asterisk n, making it highly optimal for solving maze problems. In summary, the algorithm achieves an impressive time and space complexity of O, m asterisk n, which is significantly better than naive approaches. By leveraging breadth-first search and the visited set, it avoids redundant work and ensures efficient processing of the maze. This makes it well-suited for handling large mazes, where performance is critical. The combination of systematic exploration and direct rolling to stopping points ensures that the solution is both elegant and scalable, solving the problem in an optimal manner. In this section, we'll cover some common mistakes and how to avoid them when solving maze problems. One frequent issue is failing to account for edge cases, such as when the maze has no valid path or when the start position is the same as the destination. These situations can lead to incorrect outputs or even infinite loops, so it's critical to explicitly check for these conditions before running your algorithm. Another common mistake is ignoring visited cells during traversal. If you're using DFS or BFS, revisiting cells that have already been explored can lead to redundant computations or infinite loops. To prevent this, you should maintain a visited set or matrix. Additionally, errors often arise from incorrect boundary checks, where out-of-bound indices are accessed during grid traversal. Always validate your indices before accessing the maze grid to avoid this. Lastly, if the problem asks for the shortest path, relying purely on DFS might lead to suboptimal results unless you use backtracking. Instead, consider BFS, which is specifically designed to find the shortest path in an unweighted graph. Another mistake to watch out for is overcomplicating the algorithm. Adding unnecessary layers of logic, such as multiple recursion stacks or redundant conditions, can make your code more difficult to debug and slower to execute. Focus on keeping the traversal logic as simple and efficient as possible. Now, from an interview perspective, maze problems are a great opportunity to demonstrate your understanding of graph traversal techniques. For instance, BFS is ideal for shortest path problems, while DFS is better suited for exhaustive searches. It's important to clearly explain your choice of traversal method during the interview and discuss trade-offs. For example, recursive DFS can be memory-intensive due to the call stack, whereas iterative BFS requires additional memory for the queue. Be ready to talk about time and space complexity trade-offs in your solution. Additionally, interviewers appreciate when you explicitly address test cases before running your code. For a maze problem, these might include fully blocked mazes, single-cell mazes, or scenarios where no path exists. This shows that you're thinking critically about edge cases and are thorough in your approach. Maze problems also share similarities with other coding challenges, so practicing related problems can help you prepare. For example, LeetCode 79, word search, involves backtracking on a grid, while LeetCode 200, number of islands, focuses on counting connected components using DFS or BFS. LeetCode 490, the maze, is another traversal problem with open paths, and LeetCode 127, word ladder, explores graph-based shortest path concepts similar to BFS in a maze. Beyond these problems, it's helpful to understand alternative approaches. BFS is ideal when you need to find the shortest path in an unweighted grid, though it requires more memory to maintain the queue. DFS, on the other hand, is useful for checking path existence or performing exhaustive searches, but it may not guarantee the shortest path and can be memory-intensive due to recursion. If the maze involves weighted paths, Dijkstra's algorithm is a powerful option. However, it's more complex than BFS and unnecessary for unweighted grids. By mastering these techniques, you'll have the flexibility to choose the best approach based on the problem's requirements. For even more optimization, consider using bidirectional search. This approach is particularly useful for finding the shortest path in large grids, as it simultaneously searches from the start and the destination, meeting in the middle. While it can significantly reduce the search space, it requires additional data structures and careful implementation to manage both fronts. Dynamic programming is another powerful strategy, especially for problems with overlapping subproblems, such as counting all unique paths in a maze. It uses memoization to store intermediate results, which can drastically improve performance. However, it does require extra space for the memoization table. Knowing when to apply these advanced techniques can set your solutions apart, particularly in scenarios where traversal-based methods might fall short. By understanding these trade-offs and their use cases, you'll be well prepared to tackle both standard and advanced variations of maze problems. Great job following through. We've tackled the maze and learned about key strategies for pathfinding problems. Remember to practice similar problems to solidify your understanding. If you enjoyed this, don't forget to like, share, and subscribe. See you in the next challenge. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!